Hi again. So we'll be solving exercise 1, which is to check whether a given binary tree is a binary search tree or not. So before solving this exercise, I will solve some exercise related to binary search tree, because in the lecture I just wrote the insertion of an element into a binary search tree. So we will cover here, before answering this question, how to check whether an element belongs to a binary tree, a binary search tree. So we'll solve it recursively and iteratively to find the minimum and the maximum. Again, iteratively and recursively. We will do the insertion again in both schemes, so recursive and iterative, and then we will solve this exercise, so whether it's a binary search tree or not, and we'll do one more additional exercise. So let's recall that, for example, this is a binary search tree, and then in binary search tree, if we have a root, so the left subtree, so all the elements in the left subtree are smaller than the root element, and all the elements in the right subtree are greater than the root element. And recursively, so in the left subtree, for example, here we have the root 10, so all the left subtree, all the elements in the left subtree are less than 10, and all the elements in the right subtree are greater than 10. So what we'll do now is that we'll write, so the declaration of a binary search tree is the same as a binary tree, so it's just the treatment that it changes. So how to check whether an element belongs to the binary search tree? So for example, if I want to search for 25, so obviously I will start from the root. So if 25 is greater than 50, so of course I will not search here, because I will not find it in the left part. So I need just to move to the right side. So for example, iteratively, if I have a pointer here b that points to the root node, I just need to move b to the right, and so on until I reach 25, or I don't find 25. Recursively, I just need to recursively to call this function, however, with the tree on the right side. So this is for searching. So the same is for the minimum and maximum. So in order to find the minimum and maximum, again, I will not search all the binary search tree. And again, the minimum is here and the maximum is here. So the minimum is on the leftmost part of the tree. So if I have b here, iteratively I would move b arrow left till I reach b arrow left equal to null. The same for the max, I will go b arrow right. Recursively, I just go I will recursively call the function with b equal b arrow left. For the insertion, so as you have seen, the insertion is always at the bottom of the tree, so at the end. So we have seen how we will traverse, so it's always the same. So we need to either pick one of the left or right directions, and when we reach the null at the end, we will insert the element. So it could be done either iteratively or recursively. And this is for the insertion. I will do also a deletion, so how we will delete an element, and this is the most difficult part in binary search tree. So let's start. So I have the declaration of a normal binary search tree. I have prepared some of the test cases here, so for the insertion, and I would make one for the deletion also, and I have constructed the trees, also the test cases, and we will work on that in a while. So we have also the delete, and we will test it. So let's start with the search. So I need to find an element v into the binary search tree, and I will do it iteratively. So we will start from b and we'll keep looping. So we have a while here. So as long as b is different than null, what I will do is that I will check the data. So if b arrow data is equal to v, I will return true. However, here the return value is BST, so it's the pointer. So I will return b, not null. So if it's not the case, I would go either to the left or to the right. So if the value I'm looking for is greater than b arrow data, it means I need to go to the right. Iteratively, it means that b should take the value of b arrow right, else, so obviously it would be equal b arrow left. So, and at the end, if I never return b, obviously I will return none. As easy as that. So this is for the iterative part. For the recursive part, so we don't have a while, we have a if. So if b different than null, I will do that. Otherwise, I will return null. So what I would do if b is different than null, I will check. So the same checks here. I will copy paste. So if b arrow data is equal to v, I will return b. Otherwise, if b is greater than b arrow data, I will call the same function on the right side, and I will always search for v. However, here I will call it on the left side, and I will search also for the element v. So again, it's as easy as that. So this is for the test. So I will go down and call the test function. So in the test function, let's see what we have. So test BST. So no, it's not that. So the test belongs. So I need to give x, and so this was just for the output, and I will test the iterative function and the recursive function. So let's go down and see what's in the B. So here we have a 3, and we have in the 3 10 5 2 3 9 20 40. Let's say I will search for 9, and let's execute. So there's an error here. There's something error in the input, so maybe I have in minimum BST recursive, so maybe I have we need to add semicolon in all these. Okay, let's do it. Okay, so we gave 9, so 9 is in the BST and 9 is not in the BST. So let's check what we have here. So we have a problem in the recursive part. So what we have done wrong. So if v arrow data is equal to v, I will return v. If v is greater than v arrow data, I will go to the right side, otherwise on the left side. So it's correct. Let me see. Where is the function? So in the iterative, I have recursive b and belong. We have the same task. We either return b or not b. So let us check. So if b arrow data equal to v, I will return b. If v is greater, there's missing return here. So this is always the mistake. So we always return. We should pay attention. So whenever we have a return value, we should use a return. So, and yes, it's in the BST. Let's pick another value. Let's say 900. And of course, they both will tell us that there is no 900 in the tree. So this is the task for the belong test recursive. Let's do the minimum and maximum. Again, let's do the iterative one. So as we have seen, in the minimum, it's the leftmost. So we will do a while loop. So in iterative, I will do while loop. So as long b is different than null, I will try to go b arrow left. However, I need to return b if the null is equal to 0. So if I reach the b arrow left equal to null, so if it's equal to null, I will return b. Otherwise, I will keep on moving. So b equal b arrow left. And of course, if already the b is equal to null, I will return null. So if there's no tree, I will return null. So this is for the iterative part. The same can be said for the recursive part. So instead of while, I have if. Again, if b arrow left is equal to null, I will return b. Otherwise, I will call minimum BST recursive. So return minimum BST recursive b arrow left. So this is for the minimum. So let's again write the maximum. So at the same time, so here iteratively I will go to the right side. So as long as the right side is different than null, I will go to the right, and whenever I reach b arrow right equal to null, I will return b. For the recursive part, again, so it's the same. I will go to the right. So if b arrow right is different than null, I will go to the right. Otherwise, I will recursively call minimum maximum BST recursive on the right side. So let's get down and activate the test. So let's remove this. In the test minimum maximum, let's see what we have. So we are calling the minimum and maximum in recursive and maximum. So recursive and iterative. First we are calling the iterative part and then the recursive part. So let's run. So let's go and see what we have in the 3b. So obviously the minimum value is equal to 2 and the maximum is equal to 40. So this is correct. Now let's move to the insertion of an element into the ST. So we have already done this in recursively, so we'll do it recursively and iteratively. So as we see, we know, so in order to add an element, we'll add it whenever we reach a null. So if not b, so if b is equal to null, it means, so I need to allocate a b. So b would be equal to a BST malloc size of node, size of struct node, and then so if I couldn't reserve a place in memory, so I will return null. Here we have an integer, so I will return 0. So, and then I will fill the elements, so b arrow data equal to e, and b arrow left equal b arrow right, and is equal to null, and I will return 1, of course. So this is for the base case. However, if not b, it means that I need to go either left or right. So if I found the elements that I need to add, so we suppose that all the elements are distinct. So if it's the case, I could not add the same element twice, so I would return 0. So in other cases, I can allow the duplicated, so it's okay. So I can remove those parts if there's duplicate elements in the binary search tree. So if the element that I want to add is less than b arrow data, it means that I need to add it to the left side. So I will do a return insert BST e, and here we have address of the reference b arrow left. Otherwise, I would add it to the right side. And this is it for the insertion of the in a binary search tree using recursivity. As for the iterative insertion, so it's again the same. However, here we need to pay attention that in order to add iteratively, I need to not reach the null, because if I reach b equal to null, I will not be able to link it. So I need to stay at the part where b arrow left or b arrow right is equal to null, but never where b is equal to null. So for that, we will use 2 pointers just to be one step ahead of null. So for that, so we'll use, so here we have b3. You can also use BST because it's the same declaration. I have used the type def. So we have a BST c and d, so we'll use it later, and we'll start c equal to d reference b. We'll start from c. So as long as c is different than null, I will move down, so either left or right. So I will keep here, so it's the pointer before c equal to null, just in order to allocate the c pointer later. So if c arrow data equal to e, so there's already this element, so I will return 0. Otherwise, I will go either left or right. So if the element that I want to add is less than c arrow data, so it means that I need to move c to the left side. Otherwise, I need to move c to the right side. So at the end of this loop, c would equal to null. However, in d, I would stay in the node in the previous node, so in order to link it later. So in C, I would reserve and make the reservation. So BST malloc size of struct node, and I would fill the data. So if not C, obviously I will return 0, return null, return 0. So I couldn't do the allocation, and I would place in data C arrow data equal to E, and left and right equal to null. And then I need to link all this. So if at the beginning b is equal to null, so if the tree is empty, so I'm just inserting the first element. So obviously d reference b would be equal to c. Otherwise, I would either link it to the left side or the left side or the right side. So if I want to add e is less than d arrow data, it means that d arrow left would be equal to c. Otherwise, d arrow right would be equal to c, and at the end I will return 1. So this is it for the insertion. So the new here is that I need to loop into one branch, but I need to keep the pointer to the last before node, before the null. I will do the allocation. I will fill a new node, and then I will link it. So if the tree is empty, so I would obviously do directly the allocation. However, I need either to link it to the left or right side. So let's move down and see the insertion. So I will comment this and do the insertion into B. So let's see what we have in the test. So in the insertion, first we'll print the tree, and then recursively I will insert 4, and then I will insert 19, and then I will insert delete. So I will not use delete here, so I will just do the test on the insertion. So we'll insert recursively the element 4 and iteratively 19. So let's check. So what we have here, so double, and let's run. So first we have, let's go to the test, we have the tree. So this is the tree, which is B, and then recursively I need to add 4. So let's see how we'll proceed. So 4 is less than 10, it's recursively, so it means I need to insert the 4 into the left subtree. Then I find 5. 5 is greater than 4, it means that I need to add 4 in the left subtree. And then I find 2, 4 is greater than 2, it means that I need to add 3 in the 4 in the right subtree. So here we find 3, 4 is greater than 3, it means that I need to add it into the right side. So this is iteratively, it's more easier. Let's see, this is recursively, sorry. Now we need to add 19 iteratively. So what we will do is that we'll start from 10. So we are in this tree, in the second tree. We'll start from 10, 19. So first we'll reach. So let's go up and see the tracing. So we have the insert BST. I will start from C, which equal to here, and I will either move left to right. So C, there's no data here. 19 is not on the tree. So we have the element E19 is greater than 10, so I would move to the right. So C would move to the right. And then we have 20. 20 is greater, so I need to move to the left. However, here the left, when I reach here, C is equal to null. However, D is pointing to 20. So we stop here, we allocate C, so we allocate the element 19 into a node, we put left and right equal to null, and then we check. So B is not equal to null because we already have a 3, so we check 19, so the element E is less than D. So I need to link it to its left side. So for that, we have the 19 on the left side on 20, and this is the insertion function iteratively for this tree. So we need to write the deletion. So the deletion of an element into BST is not that easy. So in order to understand it, let's go back to this tree and see some characteristics. So okay, I'm removing all these. So we have explored in the course that the Inorder Traversal of the BST, it gives us a sorted list. So what does it mean in order? It means left, root, right. So the Inorder Traversal of this tree is 8, 10, 12, 15, 16, 20, and 25. Suppose, for example, I want to delete the element 15. I want to delete the element, so I need to restructure this tree in order to keep it as a BST. So if I need to delete the 15, I need to keep this order. So if I want to place a value instead of 15, in place of 15, so it should be, there's no choices, there are just two choices. So either I should place 12, either I should place 16, because I cannot place 20 because I need to rearrange all the stuff. So what's the purpose in here? So whenever I need to delete an element, so I need to find the closest elements to the delete element, so the closest minimum and the closest maximum. So if you look well, so here for each element it's left subtree, and here it's a right subtree, and this one is the greatest on the left subtree, and this one is the smallest on the right subtree. And if you look well, so if you want to find the maximum element on this on the subtree, and as we have seen, we just need to go one right, and then we go leftmost in order to find the 12. The same can be said for 16. 16 is the smallest of this tree. So we know, we already wrote a function that finds the minimum and maximum. So the minimum, we should go leftmost. This is the pointer for the tree. So in order to reach a 20, I need to go one right. I need just one step to the right, and then I go leftmost to find the minimum on the right subtree. So this is the idea for in order to delete an element. So recursively, it's also it's a bit difficult to write. Iteratively, it's way more difficult. However, we'll write it in both iterative and recursive parts. So let me repeat. So in order to delete an element, so I have two choices. Either I will pick the maximum element in the left subtree or the minimum element in the right subtree. So what we'll do is that we will pick the left, the minimum element, the maximum element on the left subtree. It's up to you. It's just you need to how to loop. So this is for the deletion. So let's start. So I will start with the iterative one. So let me check the test and see what test we have. So iterative. So we'll start with iterative and then we'll do the recursive one. So the iterative, delete BST iterative. So what we will do that in order to delete a node, so it could be 15, it could be 20. So what we will do is that we will get a pointer on the element that we need to delete. So like the find function that we have wrote. However, we will write a function that searches for an element and returns a pointer. So we will return a pointer and then we will delete the root element. So we'll have two functions, a function that returns a pointer to the element that we want to delete, and then we will write a function that deletes the root of this function. So for the first function, find, I have already wrote it, so it's the same as the find element. However, it returns a tree, not yes or no, not a true. So for deleting binary search tree iteratively, so forcibly I need to call the function find and then call the function delete root that will delete the root element of a binary search tree. So for that we will have a B3. So we need a pointer here. I will explain it. So A is equal find BE. So I will find the element E that I want to delete in B. So find, it takes a pointer and returns a pointer. So it's very important to have pointers here. So it's a double pointer because I need to modify the root elements next. So if I just place B3 without a pointer, it means that I have a copy of the pointer in A. So this is not the option. So if A is equal to null, if A is different than null, if it's equal to null, it means E is not in the tree. So there's no need to delete the element. So I cannot delete it. I will delete root of A. And of course, this is it. And I will return 1. So delete root, it will delete the root element of the tree. So if I cannot delete the element for some reason, so usually I would always delete it. So in case that the tree is empty, for example, so I cannot delete the root. So let me repeat. So here iteratively, so I would find a pointer to the element E that I want to delete. However, I need the address of the pointer. So for that I need a pointer, a double pointer, not just an address. I need the address of the address in order to delete the element of the tree. So for deleting the root, we will start. So let's start. So if already B is equal to null, so if there's no tree, so I will return 0. Obviously, there's nothing to delete. I cannot delete the root. So if I am already on a leaf node, so for example, if I'm on 4 here and I need to delete 4, I have a pointer to 4. So what I will do, so if it's leaf, so if not B, I will write it B arrow left because here we have double pointer. B arrow left equal to null. And B arrow right is equal to null. I will just free the element, so I need to just modify some pointers in order to work correctly. So what I will do is that I will declare now a tree called C. In B I would place null and I would free the element C. So here I would use B3 C. So in order to delete 4, I would use an auxiliary pointer, so it's called C, and then I would place B equal to null. So the 3, for example, the 3 arrow, the pointers from here to the right, so it will be equal to null, and then I will free C. So this is for the where we have a leaf node. Now that's the case for we have the left equal to null, so there is no left, and for example I need to delete 20. So whenever I need to delete 20, just since there is no left, I just keep to move the right subtree up. So I just move the right subtree up. It's very easy here. So it's the same for the left or right. So if you have just one branch, it's easy. So else if if the B arrow left is equal to null, I just need to move D equal to null. So I just need to move the tree up. So C is equal to D reference B, and I need to move D reference B equal D reference B arrow right, and I will free C. So C would point to 20, B, which is the pointer to 20, it will point now to 40, and I will free C. So the same is for the case if B arrow right is equal to null. So if B arrow right equal to null, I would move all the left part up one step. So else it means that I have a left and right side. So here you need to decide. So either you find the maximum on the left or the minimum on the right. So in my code, I will find the maximum, find the max on the left. So as I have told you, I need to go one right. So I need to we would go one left and then right most till the end. So I will use C here. So C would be equal to B arrow left. So I will go one left and then I would need to go rightmost. So if it happens that C, so here we have two cases. So if C arrow right is equal to null, so it happens that, for example, I'm going to so we don't have an example here where we have left and right. However, for example, if I don't have, I'm here in 5. No, there's no example here. So if C arrow right is equal to null, so what I would do that, so the C arrow right is the maximum. So for example, if I'm in 10 and I need to delete 10 and I have here just 5 and 20, so there's no 9. So obviously I need to get up 5 from to here. So it's obvious because there's no 9. So there's no way to find a 9. So what I would do is that in B arrow left, to be equal to C arrow left. So I'm just moving the pointers and also I'm moving the data, and then I will free C. So I move the left pointer, I will move also the data, and then I will free C. So this is if the right is equal to null. If the right is not equal to null, I need to loop. So else while C arrow right is different than null. Okay. So again, so as we have done, we need an additional pointer. So just to wait, so to have a pointer on the last before null pointer, and C equal arrow right. So when we reach here, it means that C is equal to null. However, D, it points to the last before. So in B arrow data, so this is the root element of the tree that I want to delete. So I place the data of C arrow data. And for D arrow right, because D is not equal to null, it will point to C arrow left. And I will free C. And of course, at the end, I will return 1 since everything would be okay. So it's not that easy, I know. There's a lot of cases and it's not obvious to test it. So let's get down and see the test. So I need to, we don't have delete here. So let's delete 19. So look well, so there's no 19. So I will try with different values. Let's delete 20. So in place of 20, I've got 19. So we have tested the case where we have left and right. So we got the 19, and that's it. So we have shifted the tree up. Let's, for example, pick 10. So in 10, I will get 9. So I will get 9. So look well. Let's delete 2. So when deleting 2, I'm just moving up the tree. Let's delete 5. So in 5, I get left and right and right. I get 4. and I have adjusted the pointer. So this is for the deletion of the binary search tree, the element. So you need to review it. So the code of the function is not available online, and it will not be available online. So you need to follow this video and try to rewrite it and to check it by yourself, and again to make the trace. So let's move now to the deletion of a BST recursively. So in order to do that, we need either to go left or right, so it's easy. So we either go to the left, to the right, depends on the value of we want to delete. And whenever we reach the leaf node, or it's a leaf node, so we need to replace it with its largest of its left or right subtree. So here we chose the left subtree, and if it has one child, we need to do the variation. So it's the same like in the iterative part, so we know how to transform it now. So let's start doing it. So if the BST is null, so if not dereference B, I will return 0. So if the element that I want to delete is less than B arrow data, it means that I need to go to the left, so I need to delete something from the left. So I didn't reach it yet, so delete BST recursive. We have the element E, and here we have the address. So let me pick it from somewhere because it's very easy, very difficult to write it. There's a lot of brackets. So I need to delete it from the left, otherwise I need to delete it else. No, I don't know. We delete it from the right side. So whenever I'm here, it means that I have E equal to dereference B arrow data, so else. So let's call it if, it's better. So if, because here we have so the else is greater or equal, so let's here have greater, and in the else we will have the condition where E is equal to B arrow data. So what we will do that, we'll check. So if we have both left and right, so if B arrow left is different than null, and B arrow right different than null, so we need to find the maximum on the left subtree. So for that we will call the function. So we already wrote it, so we will need a temporary value. So temp would be a BST. So temp would be to find recursively the maximum, so max, it's called max BST recursive, and on the left subtree, so we find a pointer to the node, to the maximum node on the left subtree, and we switch the data. So B arrow data would be equal to temp arrow data, and recursively we will delete the root node of B arrow left. So delete BST recursive, address of B arrow left. However, here we have temp arrow data. So recursively we will delete the node that we want to delete. So it's very easy to view that. So else, so if there is just one node, so there's one child, or maybe it's a leaf, so we need, so temporary would be equal to dereference B. So I just need to move the element. So we need to check if the left or right part is null. So if arrow dereference B arrow left is equal to null, it means that I need to link it to the right. So dereference B would be equal dereference B arrow right. Otherwise, else, if B arrow right is equal to null, I would move it to the left. And of course, at the end, I would free temp. And again, I will return 1 at the end. So let me repeat. So in deleting recursively, so I would either delete from left or right, and then here we have return. So we have if both left and right subtrees exist, so I need to find the recursive, the maximum on the left side. So I have a pointer. I would switch the data between B and the temp, and then I will delete temp from the left subtree. So otherwise, if I have one of the two pointers or so just of the two pointers, so I would either link it to the left or the right. So let me copy the prototype. So it's BST recursive. So and we'll delete one of let's delete 5. So we have here. So let's keep it. Oh, we cannot delete it both. So let's run. It will be the same. So let's delete 4. So 4, we have 4 here. So it's easy. Let's delete 10 recursively. So obviously I will get 9 and I will keep the same tree. So this is it for the deletion. It's not an easy operation. I know it's very difficult to write the deletion of an element BST either iteratively or recursively. So we still have two stuff to cover: find the smallest cased element and to solve the exercise. Before solving the exercise, let's check the case smallest element. So let's again return to this lovely example. So we have a BST, and also so we need to know what is the case smallest element. So for example, if I want to ask you what is the third smallest element, so maybe you will say, okay, I will find the minimum element, and then I will delete it from the tree, and then I will find the minimum element. So for example, here I'll find 8 and delete it, and then 10 I will delete it, then I will find 12, and you will say, okay, this is the third minimum element. So obviously it will be too cumbersome and the complexity will be very high. So another way and a more effective way is to use the well-known property of a BST, is that the in-order traversal of a BST, it gives us a sorted list. So it gives us 8, 10, 12, 15, 16, 20, and 25. So it's easy if I do a traversal and I have a counter, and when I reach 3, so I would return the value. So this is what we will do in this function. So we have a function called case recursive. So in order to do the case recursive, I need a count. So I have here the BST, and we have k, which is the number of minimum element. And of course, in order to solve that, I need to load a helper function that takes one additional parameter, which is a pointer to count. Count is the counter. So as we have seen here, 1, 2, 3. So I need to keep the counter, and I will increment this counter as long as we do the recursive. So as we know here, we just need to implement the in-order traversal. So left data and then right. So as easy as that. So let's do it. So if not B, so if the tree is empty, so this is the stopping condition. So here we need to return a pointer, so we return null, and then we need to go to the left. So in order to go to the left, and the function returns BST, so I need to the return value, so it be a BST. So left, just the call. So in left, here I would keep the count because I didn't increment it, I didn't visit it yet, the root node. K would remain the same, and here I just need to go to the left. So in left, so it's either a pointer or it's either I found the element or I didn't found it. So if not left, so if left different than null, it means that I found it, so I return left, as easy as that. So for example here, if I want to find the left 12, so when I go back, when I reach back to 15, I will not go to the right side because I already found it, so there's no need to go to the right side. So here it means that I have reached the data, the node, so I need to increment the number of counts. So if plus plus dereference count is equal to k, it means that this is the number that I want. So I return the pointer to the tree, so I return B. Otherwise, so here I will move to the right side, so it's right. So let me repeat. So this is the in-order traversal, this is left, this is root, and this is right, and those are very easy. So when I increment the count, I increment it when I'm on the root. element. So if I'm on the root, I will, and I found it, I will return B. So I can return 1, for example. But however, I need to find the element. So I can return the element. However, it's better to use a BST. So let's test it and see what we have in the test. So where is the test? So I will test case smallest. Okay, so we need to give x, which is k here, and we need to call it. So let's say 4 and execute. So let me print the tree. I don't know from where that is comma. So let's print before the tree. Print b, just to know the 4. So I need to the first element. So the first element is equal. So this is 1, 2, 3, and 4. So it's equal to 9. So let's say 1. It will be equal to 2. Okay. 23. And there is no element, so we have something. So we need to check 6. So it's equal to 20. So this is for the case smallest. And now we can move to our question, which is about how to test the BST. So let me check the test function first. So test BST, we have test BST, so all the tests. So we have a binary search tree here. It's a binary tree, and we need to check whether it's a binary search tree or not. So I repeat, for a binary search tree, all the elements on the left part should be less than the root, and all the right part should be greater than the root, and recursively. So in 2, all the elements on the left are less, and all the elements on the right are greater. So obviously here we have this is not a BST. However, the code here, it will give us a true. So let's check it first. So they are telling us that the stopping condition, if 3 is equal to null, I will return 1, which is obvious. And then I will check if 3 arrow left different than null and 3 arrow left arrow data is greater than 3 arrow data, I will return 0. Okay, so for example, we don't have here, so we have the second part. So if 3 arrow right is different than null and 3 arrow right data is less than 3 arrow data, I will return a 0. So obviously it's not the case here. So, and I will check if not BST 3 arrow left and not BST 3 arrow right, I will return 0. Otherwise, I will return 1. So let me repeat. First, we'll check if we have a violation. If, for example, we have here 6. If you have here a smaller number than 6, or if you have here a greater number than 6, I will return 0. This is both case here. Otherwise, I need to check the left subtree and the right subtree. So obviously, there's an error here. So let's check. So I'm calling the function here, the BST, which is C. So C is the same example as here, 62198. So I'm calling on BST C. I will just do that. So in order to check that, it will give us true. So is BST wrong? Because I'm calling it wrong. So this is the function BST wrong, and it gives us true. However, this is not a BST. So the question is, think of getting the correct algorithm. How can we solve the problem? So as you have seen in this part here, we have just only checked the direct elements. So we have compared 6 to 2 and 8. We didn't compare 6 to all the tree here, to all the elements on the left subtree and to all the elements on the right subtree. So this is the error here. So we didn't check 6 with all the elements. So what we could do is that we will not check 6 with all the elements. So 6 should be, so the maximum element in the left subtree should be less than 6, and the minimum element on the right subtree should be greater than 6. So instead of doing this, we just need to rectify. So instead of 3 arrow left arrow data, I need to find the maximum on the left, and here we need to find the minimum on the right. So here is the solution. So I just need to modify. So I need to find the maximum on the left and the minimum on the right. So let's now uncomment this and see the output. So of course here BST is equal to 0. So let me call the B. So B is a correct BST. So let me call it B. So let me here. So in B, So it's correct BST, so we have is BST. So this is wrong. So we cannot use the function, so because we are not comparing all the elements. So however, in order to, so this is it for the question, because this is question 1, and for the part 2 they are telling us, okay, you can do that, you can use two functions, find min and find max, but however the complexity is very big. So one way to do that is that you can use the in-order traversal. So again, I come back to the in-order traversal, because in in-order traversal I can, when doing in-order, I end up with a sorted list. So I need just, when doing the in-order traversal, and if I found a violation, so if the list is not sorted, it means that this is not a BST. So this is the version 2. So I will go down just to see the prototype and explain why we have this. So in the prototype for the SBST version 2, so we have the tree and we need also a previous. Why we need the previous? Because while doing the in-order traversal, I need to check 12 with 10. So I'm in 12, so I need to keep track of the older elements of the previously checked elements. So this is that, and this is it, why we need a previous. So obviously I will start from a very minimum element. So here I'm starting with int min. So of course the first element will be greater than int min. So this is it, why we are using a previous. So again, it's the same as we have done in the case recursive. We need to traverse left, then the data, and then the right. So let's write it. So the part 2 was a question, a part of a final exam. So if not B, I will return 1. So it means it's everything okay, I have reached the end and the list was sorted. Then I would call BST on the left, so I will call it here. Then I will do the check the return value, so B arrow left. Okay, we forgot the B arrow left, and then we have previous. So we need, here's the return, int, it means either 0 or 1. So directly, if not BST, not is BST version 2, I will return 0. There's no need to continue. It means there's something wrong. And then here we have the return, the test on the data. So if B arrow data is less than previous, it means here there's a violation, I will return 0. Otherwise, I would save the element in previous, which is equal to B arrow data, and I will go and check the right side. So return is BST version 2, right. As easy as that. So let's check. I have uncommented that. So we have B. B is correct. So we should have is BST version 2 equal 1. Let's check C, what we will get. So firstly we'll get 0, because if I do in an order traversal, I will end with 12968. So again, it's not a BST. So this is for this exercise 1. So I know it's a bit difficult. So if you have any problems or questions, do not hesitate to write to me. And please don't write to me to get the code of the insertion and deletion. So make sure to write it by your own. And again, thanks for watching.